If we visited Pluto's primitive appearance, it might reveal a surprising landscape. Volcanoes expelling water instead of lava. A liquid ocean stretching from horizon to horizon, full of exotic life forms. Billions of years ago, Pluto may have really been like this. However, over time, its interior gradually lost heat, and the energy provided by the sun was not enough to maintain its temperature. As a result, Pluto's surface became covered by layers of ice. Even so, Pluto did not completely freeze. Beneath its thick, icy crust, there is still a liquid ocean. Moreover, signs of volcanic activity can be found on its surface, suggesting that Pluto might be slowly returning to its original state, and perhaps even could harbor life again. However, to truly understand the entirety of Pluto, we need to uncover its hidden secrets. Pluto's formation dates back to approximately 4.6 billion years ago, almost at the same time as Earth. Today, its surface area is comparable to that of South America, but in ancient times, its size was about 2.5 times larger, nearly entirely covered by a liquid ocean. However, we know that Pluto is located about 40 times farther from the Sun than Earth. The existence of a liquid ocean at such a distance seems to challenge logic. To solve this mystery, we need to look even further back into the past. At the beginning of the solar system, scientists believe that the planets formed within a protoplanetary disk around the young Sun. This disk was a flattened ring of material orbiting the star, which is why most of the planets in the solar system follow orbits in approximately the same plane. However, Pluto is an exception. This happens because the orbits of the planets can change over time. Scientists assume that Jupiter, Saturn, Uranus, and Neptune formed closer to the Sun than their current positions and later migrated outward. During this process, Neptune, as it moved away from the Sun, gravitationally attracted some smaller bodies, including Pluto, pushing them away from their original orbits. This means that, at the beginning of its existence, Pluto was closer to the Sun, allowing it to receive enough heat to sustain a liquid ocean. Additionally, its primitive atmosphere was 40 times denser than Mars's, but today it is only 100,000th of Earth's atmospheric density. This thin atmosphere only becomes visible temporarily when Pluto gets a bit closer to the Sun, causing part of its ice crust to evaporate. Without a significant atmosphere, Pluto's surface cannot maintain stable liquids. However, Neptune wasn't the only factor shaping Pluto's destiny. The presence of one of its moons, Charon, also had a profound impact on its environment. Charon has a diameter that is half of Pluto's. The most interesting thing is that one side of Charon is always facing Pluto. In the Pluto-Charon system, the moon does not orbit Pluto in the traditional way. Instead, both revolve around an imaginary point called the barycenter. Charon formed about 4.5 billion years ago, about 100 million years after Pluto was born. Scientists believe that a high-speed collision between Pluto and a body from the Kuiper Belt was responsible for the formation of Charon. This impact caused drastic changes to Pluto's surface, forming the famous region known as Tombaugh Regio, Pluto's heart. This region is a vast glacier rich in nitrogen ice, stretching over 1,590 kilometers. Scientists believe that, billions of years ago, a subterranean ocean of liquid water existed beneath Pluto. The impact that formed Charon may have caused some of this water to emerge, later freezing and creating Pluto's ice crust. As a result, Charon's surface is primarily made of water ice, while Pluto is covered by nitrogen ice. The collision also caused Pluto's peculiar rotation. Today, its axis of rotation is tilted by about 120 degrees, compared to Earth's 23 degrees. This extreme tilt means that Pluto's polar regions go through cycles of darkness and light lasting 124 Earth years. However, the consequences of this impact were not limited to Charon's formation. In 2011, Brazilian scientists calculated that Pluto could have a ring system, although much smaller than Saturn's, about 750 times smaller and much more tenuous. A 2013 study suggested that Pluto might also have up to 10 natural satellites. However, when the New Horizons spacecraft sent back images of Pluto in 2015, scientists were surprised by their findings. They were surprised to discover that Pluto does not have a ring system or new satellites, only the 5 known satellites: Charon, Nix, Hydra, Kerberos, and Styx. Alan Stern, planetary scientist and lead investigator of the New Horizons mission, considers the absence of rings and new satellites one of the most surprising discoveries of the mission. However, retrieving ice samples from Charon's surface or the Tombaugh region could lead to even more impactful discoveries. If the ice on Charon's surface was once part of Pluto's liquid ocean, there could be traces of life there. Pluto's exploration has raised even more questions for scientists. For example, upon closely observing certain areas of the planet's surface, one can notice fractures with peculiar shapes. These fractures, called ice spiders, are unique geological structures on Pluto's surface. Some of these cracks extend from north to south for up to 580 kilometers. The most surprising thing is that this spider structure is similar to formations found on Venus and Mercury. Scientists believe that these fractures might have been caused by the expansion of Pluto's ice crust due to internal heat, in a similar way to what happens when magma from a volcano rises and lifts Earth's crust. However, since Pluto does not have hot lava, it does not form volcanoes in the traditional sense. Still, images from the New Horizons spacecraft revealed that there are volcanic formations on Pluto's surface. In the southwest of Sputnik Planitia, there are two mountains called Wright Mons and Picard Mons, which are, in fact, ice volcanoes. Despite Pluto having an average temperature of -230 degrees Celsius, these volcanoes do not expel molten lava but rather a mixture of water and nitrogen ice with a consistency similar to toothpaste. Pluto's largest ice volcano, Picard Mons, is about 7 kilometers high and has a crater 250 kilometers wide, a size comparable to Earth's largest volcano, Mauna Loa in Hawaii. However, Pluto is only 1/6 the size of Earth. Scientists estimate that these ice volcanoes formed about 2 billion years ago, and that the most recent eruption occurred only 100 million years ago, which, in astronomical terms, is relatively recent. However, the ice volcanoes are not the strangest geological phenomena on Pluto. In the west of Sputnik Planitia, the surface of the dwarf planet resembles a giant lava lamp. The ice blocks in this region range from 16 to 48 kilometers in diameter and are in constant motion. Their edges are covered in rough ice, while their centers are exceptionally smooth. This happens because solid ice, when heated by Pluto's internal heat, becomes lighter and rises to the surface, where it cools and sinks again, repeating this cycle. This process is estimated to take 500,000 years. The activity of ice volcanoes, the cracks on the surface, and the constant movement of ice layers indicate that Pluto is undergoing a heating process. But where does this thermal energy come from? Pluto is about 1 billion kilometers from the Sun, and sunlight takes about 5.5 hours to reach it. Even on its brightest day, the lighting on Pluto is equivalent to the brightness of a full moon night on Earth. Still, Pluto receives a significant amount of solar radiation. This happens because its extremely thin atmosphere offers no protection against this radiation. As a result, we can see some peculiar landscapes on its surface, such as mountains with textures resembling snake skin and rocks that seem to have been corroded. The ice that forms these structures does not melt and turn into liquid under sunlight. It sublimates directly, leaving unusual patterns on the surface. Although solar radiation can shape Pluto's terrain, it does not explain the existence of subterranean liquid oceans. Scientists believe that a liquid ocean may have existed beneath Pluto's surface for billions of years. When Pluto formed, it was not as cold as it is today. Its core possibly generated heat through the decay of radioactive elements, which warmed the dwarf planet's interior and kept a liquid ocean beneath its ice crust. This ocean could be up to 150 kilometers deep, covered by a 300-kilometer thick ice layer. Over time, Pluto cooled, and part of this ocean froze. Since water expands as it freezes, this might have caused the formation of fractures in Pluto's crust. Additionally, impact craters on Pluto are different from typical craters found on icy surfaces. Normally, when a meteorite strikes an ice surface, it forms a circular crater with well-defined edges. However, most of the craters on Pluto have irregular edges, as if they had been stretched. This could indicate that there is a liquid water layer still beneath the dwarf planet's surface. Another curious phenomenon on Pluto is the presence of floating ice mounds. These hills, about 500 meters high, are located in the nitrogen ice glaciers of Tombaugh region. Scientists believe that these ice mounds might move because the ice layer beneath them is periodically heated and displaced. This suggests that Pluto's subterranean ocean may not have completely frozen. The force that prevents this ocean from completely freezing might be Charon. Pluto and Charon form a binary system, where both exert gravitational influence on each other. The distance is 195,000 kilometers, just 1/20th of the distance between Earth and the Moon. Therefore, the tidal effect of Charon on Pluto is particularly significant, becoming an essential force in maintaining the internal activity of the dwarf planet. Tidal heating, simply put, means that Pluto's orbital motion and rotation generate friction inside, producing heat. This heat is not enough to make Pluto a habitable world for humans, but it might be enough to keep its subterranean oceans in a liquid state. And where there are oceans, there is the possibility of life. It might seem unbelievable, but Pluto truly has these conditions. One of the strongest pieces of evidence is the presence of rubrum crystallum, red crystal, which is not a real whale, but a region near Pluto's white heart, known as Cthulhu Macula. Located near Pluto's equator, this area spans about 3,000 kilometers and is covered by unique red deposits, hence the name. Scientists believe that this region formed over time due to the impact of Charon's progenitor body on Pluto. Associate professor at the Tokyo University of Technology, Hidenori Genda, studied this impact and ran computational simulations. His calculations suggest that after such a violent collision, the oceans near Pluto's equator would have heated up significantly. Over time, these oceans cooled, forming complex organic compounds on their surface, giving the area its reddish hue. These substances, called tholins, form when methane interacts with ultraviolet radiation from the sun. Some researchers believe that tholins could be precursors to the chemistry of life. In 2009, Professor Sergio Pilling from the State University of Paraíba in Brazil led a team of scientists in an experimental study. They bombarded tholins with F radiation and observed the formation of nucleotides, the building blocks of DNA. Imagine if Pluto's temperature were more moderate. We might find life there? For Pluto to have ideal conditions for life, we would need a much larger sunday currently. The Sun is a relatively weak yellow dwarf star, but in less than 1 billion years, its luminosity will increase by 11%. In 7.5 billion years, it will expand to 200 times its current size, becoming a red giant. By that point, the Sun will have grown to the orbit of Saturn, consuming Earth. However, on Pluto, temperatures might rise to a comfortable 20 degrees Celsius. However, Pluto's low gravity, only 1/12 of Earth's, would make it difficult to form a stable atmosphere. Over time, gases would escape less to space, but atmospheric pressure would still be much lower than Earth's. Another factor to consider is that Pluto rotates nearly on its side, with an axis tilted nearly 90 degrees. This means that its polar regions experience nights lasting 124 years. During these long nights, temperatures could plummet dramatically. However, since over 80% of Pluto's surface may be covered in water, its temperature would remain relatively stable due to low gravity. This would create challenges for flying animals, as their wings would have difficulty sustaining them in the air. Land animals would evolve to have lighter and more flexible bones. With little solid land, herbivores would struggle to survive, but predators could thrive. For example, a species called Pluto bears could feed on small fish and other hunters. Due to low gravity, land animals would likely use jumping as their primary means of locomotion, evolving hind limbs similar to those of kangaroos. Additionally, Pluto's animals might not need ears, as sound would propagate very slowly in their rarefied atmosphere. They would rely more on smell and vision. Pluto's thin atmosphere would provide a shorter visual range than on Earth, but distant objects would appear sharper, as there would be no atmospheric haze obscuring the view. Besides Pluto bears, there could be other predators, such as Pluto wolverines. These animals could have greenish fur to camouflage themselves in the landscape, as Pluto's atmosphere contains a lot of nitrogen, giving the ground a greenish tint. Pluto wolverines could use this camouflage to avoid predators and capture prey more efficiently. These animals would likely be agile both on land and in water. They could develop membranes between their front and hind limbs, allowing them to glide between mountains and swim quickly to hunt fish. The ability to glide in the air would help them escape from Pluto bears, while fast swimming would facilitate hunting. During Pluto's long winters, land predators could enter a state of hibernation, called a pause period, to survive food scarcity. This is because their aquatic prey would migrate to the planet's illuminated hemisphere. However, Pluto's surface would not be completely inactive. During prolonged darkness, a creature called the ice spider would take control of the terrestrial ecosystem. Unlike Earth spiders, ice spiders would not spin webs. Instead, they would be scavengers, feeding on the remains of other animals. However, with food scarcity, they would need to become predators. Equipped with excellent vision and specialized legs, these creatures would hunt Pluto wolverines in their winter dens. They would move in groups, using paralyzing venom to immobilize their prey before devouring them. The greatest diversity of life on Pluto, however, would be in the oceans. Over the course of evolution, local fish could develop special organs to escape predators. For example, some species could have gas sacs that, when compressed, release jets of liquid to propel them quickly away from danger. Most marine predators on Pluto would adopt ambush strategies. One example would be the Pluto anemone, which would attach itself to rocks, releasing paralyzing toxins to capture prey. Other creatures, however, would use different methods, such as the red whale of Pluto. These enormous aquatic beings would have extra limbs, making them extremely agile. With multiple rows of sharp teeth, they would be nearly unbeatable predators. Normally solitary, red whales would form small groups during reproduction, sharing food among family members. Their young, very vulnerable, would be protected by adults until they were strong enough to defend themselves. In 7.5 billion years, Pluto may regain the environmental conditions of its initial formation. And perhaps not only animals will inhabit this world. When the sun becomes a red giant and engulfs Earth and other inner planets, humanity will have only one option for survival: migrate to the outer reaches of the solar system, who knows, maybe even to Pluto.